So let us refresh the ideas of L'Hopital's rule that helps us to take care of various examples that deal with undeterminate forms 0 over 0 that could be turned into infinity over infinity or vice versa. So trying to do problem of this kind, I can, for example, start with exercise 21. And if you try to do some of problems in this group of exercises and want me to look at some of those, just tell me which one, so we'll work it out together. So at this stage, I look at the sine 3x over sine of 5x. That's the limit we need to take. And I know that sine of 0 is equal to 0. In other words, when I have x that turns into 0, then we're gonna end up with 0 over 0 undeterminate form. If you replaced x with zeros, you will get sine 0 over sine of 0. So since it's a 0 over 0 undeterminate form, I can say that derivatives of these functions could be taken, and the result is going to be the same limit. So the limit when x approaches to 0 is going to be the same if I take derivatives, and derivative of sine is a cosine of 3x, and the chain rule will make me times this by 3, right? By derivative of 3x, so it's 3. And analogously with the denominator, so it'd be cosine of 5x, but now it's multiplied by 5. So these cosines will turn into what? As a cosine of 0, which is equal to number 1 cosine of 0. And that's why we just get 3 on the top and 5 on the bottom of our fraction. So using L'Hopital's rule is pretty straightforward for that type of exercise. And sometimes you have to use it more than once, but eventually whatever dominates will give you the answer. Like, for example, if I take a look at exercise number 19, you can see that you could probably take 4 times derivatives of this, but I can say that this is equivalent to x to the power of what dominates here? Numerator, right? So it's like x to the power of 7, and when x approaches to number 1, well, it's not going to go to infinity, so maybe it's a good idea to actually utilize the L'Hopital's rule. In fact, I think you will utilize it only once here, because that 1 is going to disappear. So for a problem like number 19, you probably really want to use this property, because if you start to factor and cancel, well, this is going to probably take you a little bit longer time than just taking derivatives of your numerator and denominator, right? So that's another 0 over 0 undeterminate form, because you have 1 minus 1 on the top and 1 minus 1 on the bottom. And that's why, again, I'm going to take derivatives and get the answer much faster. So this is going to be taken the derivative of the top, which is going to be 11x power of 10, and taken derivative of the bottom, which is going to be 4x to the power of 3. And since x approaches to 1, then we get just 11 over 4 for our answer. And otherwise, it'd be kind of difficult to deal with this equivalence stuff because we use it when x approaches to infinity or to 0. But since x approaches to 1, that's not the way to go. Even though problem like 21 and calculus 1, people usually utilize that special limit. This is first special limit, sine x over x, right? But again, taking derivatives is alternative, so you can definitely utilize it. So what is alternative? In other words, you could take those limits other ways as well. And last time we saw some special set of exercises that you definitely need to utilize this L'Hopital's rule procedure using the logarithmic limits. In other words, if you have y, then you can say that e to the power of ln of y is the same thing, right? E and ln will cancel. And also, if you take a limit of y, then you can write this as a limit of e to the power, but that's a continuous function, and that's why you can just take a e to the power of limit of ln of y. So that's basically what we saw once and utilized. So I can try to do this again. Now, x could approach pretty much anywhere, so I can say just letter A, because sometimes we go with a 0, sometimes with some other number. So I can just say it doesn't truly matter. And I'm talking about the next group of exercises. You can see there's 0 or maybe infinity or maybe something else. So let me try one of these exercises and use the ideas from above. How about problem 51? I nicely underlined it. So let's try limit when x approaches to infinity. So here we have to take a look at function x to the power of 1 over x. So this type of function we definitely don't work with. And so x here goes to infinity. Notice 49 is kind of similar, but x approaches to 0. So you really want to pay attention what x is approaching to, because the answer is not going to be the same. So what we are going to discuss is the fact that it could be treated as a limit of y, and then what we're gonna do is write that x to the power of 1 over x is the same as y, and then apply logarithm in order to put that power on the ground. So logarithm of any base, well, people usually utilize ln. So the formula will be used in here. And after this step, you get to see that 1 over x is now multiplied by ln of x. And my intent is to actually find the limit of ln of y, and that's exactly what we're gonna utilize after we found it, raise e to that power. So notice that if I take a limit of this So this is equal to y. So I can write that limit of y is the same as a limit of x in denominator, ln x in numerator. And when we approach into infinity, you end up with a 0 with infinity divided by infinity, right? Denominator is clearly infinity, and ln of x when x approaches to infinity is also infinity. So here's the spot where I apply L'Hopital's rule and end up with a nicer function in my limit. So I'm gonna have 1 over x on the top and 1 is on the bottom. It looks like when we have x that goes to infinity, then 1 over x, let me write it a little bit nicer. 1 over x is going to approach to what? 1 over big is small, so 1 over x is approaching to 0. Therefore, the limit that I have here ends up being 0, right? So we are not done yet, but we know that limit of y is equal to 0. Actually, limit of ln of y. So here I wasn't careful. Limit of ln. I somehow lost ln. And then we got the answer coming out. So it's ln of y. And we just need to put it into e to the replacing this with a power which is equal to 0, and this is 1. So it turns out that x to the power of 1 over x is actually equal to 1 when x goes to infinity. You could verify it by taking the graphing calculator. There's a free graphing calculator that you can find on Google. Just type graphing calculator, and this one is not free. This one is probably over $100. But the one on the left, the Desmos, is totally free. So once you enter something in it, you want to use this lower. Here's a little keyboard, right, on the bottom. That's the one that I have to click on to be able to start entering data. Some reason they decided to put it like that, but it's free, so we should not complain about it. So let me take x and raise it to the power of 1 over x divided by x, and look at the graph. So when you say, oh, I could technically do those limits using the graph, technically, yes, if you're not asked to show any work, you're just asked to give a limit, but that's a quick way to verify. Notice that if I zoom out, the graph keeps going kind of parallel to the x-axis, and notice that it's probably approaching to 1. It's not obvious from graph, but if you already know that limit is 1, then definitely it's approaching to 1 from the top, and that's indeed what we just found out. So the limit of y happens to be 1. So logarithmic approach And then L'Hopital's rule takes care of exercises of this kind. So I think it'd be a good idea that you try to do this exercise again before next time, and maybe try to do another one similar to this and see if you can get the answer. And if not, we'll do more of these. Just let me know how it works, because I know it's been a break, and after break, people forget things. So maybe a good idea to refresh a little bit. And I'd like to take a look at the last section of chapter 8. That is pretty nice section, but even though exercises seem to be very straightforward here, but it's very useful in the next chapter. Turns out this taken so-called improper integrals idea is something that is somehow related to what we're going to do in chapter 9. So, point of story is that we cannot plug in infinity instead of one of our limits. So what they're looking for in this section is integrals that have one of their limits equal to infinity. Like, for example, on the picture, figure 8.17, what they do is they are trying to calculate the integral from 1 to infinity. And there is a function 1 over x squared. So you can find antiderivative, of course, and that's what they did in here. It's minus 1 over x. But then how would you replace your infinity into the upper limit using fundamental theorem of calculus? And the answer is they found a way. What they did is, instead of going with infinity, they actually going with some number b. So they say, what about if we integrate up to some number b, but then we send that number b to infinity? Because number b I can plug into the antiderivative. And that's what they actually did here. And then I'll take the limit when b goes to infinity, and it happens that 1 over b will go to 0 in this particular example, right? 1 over infinity is like 0, disappears. And what's left is just number 1 that was sitting next to in the parentheses. And this is a little trick, and that's what they're talking about. So instead of infinity for upper limit, you can put some number and then send this number to infinity. So instead of taking the limit of the integral at infinity, you take in the limit when your number b approaches to infinity. And doing this, we just use fundamental theorem of calculus, get the answer, and then calculate the limit. So these little steps is something that we already very familiar with. And for that matter, I can definitely work with the area of infinite region. And that's the key idea. So you can find definite integral that corresponds to the area of infinite region. And if you get a finite number, then people say word converges. And if number is infinite, then we say it's not convergent, so it's diverges. So that's specific of this section. So let us try to do this with exercise like number 20. It says integrate from 1 to infinity. So let me write it once. the way we could do the whole thing carefully. So when you're trying to find integral from 1 to infinity of some function like 3 over x raised to the power of 5 in denominator, x to the power of 5 dx, then what you're going to do is get the limit instead. So I start at 1 and go to number b, but that b I send to infinity. You see the trick? B goes to infinity rather than plugging in infinity will be replacing it with a b. And then I can write this as a power. So we use antiderivative with a favorite power rule. So the 3 will be multiplied by -5. Oh, sorry, I use derivative formula. Antiderivative puts it in denominator. See, has been too long of a break for me also. So x power of -4, right? We add 1, and then I put same -4 in denominator. So we use fundamental theorem of calculus 1 to b, and there is still that same limit. So what should I take a limit of? Well, 3/4 I can take out. It's not participating in this calculation. So it's 1 over x to the power of 4. So I can say it's 1 over b to the power of 4 minus 1 over 1 to the power of 4. So just -1, right? So that's what I have to try to find the limit of. Please double check. And b is approaching to infinity. So first piece just goes away because that's 0. And now I can find the answer to this exercise, right? It looks like we're going to have 3/4, right? I'm just wondering, why did they put -3? I think I wasn't careful. I just, for some reason, put -3. It's +3. So this is actually be -3/4 because that's the area. It should be positive. So, excuse me, -3/4. I'm going to multiply by the limit, which is, in this case, -1, right? So the limit of -1 over 1 is -1, and the answer is 3/4, just like that. So we've got this little trick performed. So one can say, Alex, looks like then all of these 1 over x things will disappear because they, when x approaches to infinity, turn into 0. Well, not so fast, because as usual, there are various possibilities to watch out. So I'd like to do one more here to illustrate you that. This is like number 21. It seemed to be analogous kind of exercise, but it is not really an analogous answer. So I can right away put a limit and then integral from 1 to b, and at b, they like b for some reason in this section. You can use any letter you like, but don't use x because x is already taken. So it's 3, and it's a cube root of x, so the power of x is 1/3, right? 1 over 3 dx. So when I be taking the antiderivative here, I'll get a 4/3, right? So 3 will be divided by 4/3, and x will be raised to the power of 4/3 from 1 to b. So the point is that x is not going to be in denominator. X actually is going to be and numerator. So 3 is flipped. So we got 9/4. I can take it outside the limit sign. And we take this limit of, now I plug in b. So it'd be b to the power of 4/3 minus 1 raised to the power of 4/3. So when b is still approaching to infinity, then this goes to infinity, right? So b to the power of 4/3, the bigger is b, the bigger is the power of 4/3, because this power is actually going to be b times, well, I say, how do you know that? Well, you can think of it like that, b times b to the 1/3, which is cube root of b. So you already see that this goes to infinity, because b approaches to infinity, times something that also goes to infinity. So it is indeed infinite. 9/4 don't change my infinity. So some of these will be divergent. So I deliberately don't want to use the word conversion, because we actually can find the integral. So if it is 3/4, then I put 3/4. Yes, it is finite, so it is convergent. But it turns out that sometimes we get infinite results. And next chapter will be trying to observe and see when exactly these are infinite and when they're finite ones. So besides one limit equal to infinity, we can have both limits infinities, like in exercise number 31. So we're gonna do pretty much same thing. Excuse me. So pretty much same thing we're gonna do. Instead of just b on the top in our limit, we're gonna put and b on the top and b on the bottom. So that way we can take care of problems like 31. So this is from minus to plus infinity. And when we're looking at this integrand, you probably recognize that it's one of the arc functions. Remember the antiderivative that resembles this, or has been too much of a break. So b goes to infinity. What arc function is that? So integrate from minus b to plus b. And 4 could be brought on the outside. And then we have 4 squared plus x squared. Arc tangent, right? Arc tangent is here for us. And x is divided by 4. And we bring 1/4 on the outside, and there is another 4 will be still present from before, and minus to plus b, and we'll also have a limit to take when b goes to infinity, right? So what about arctangent function? Isn't it odd function? You remember graph of function arctangent? In between of negative pi over 2 and positive pi over 2. It's like tangent, but just one piece of it. So looks like that. Odd function. Since we integrate from minus to plus b, then we get the same result. So this is going to be canceling each other out, right? So if you take minus b and plus b, then upper area will be the same as lower area, but the upper is positive and the lower is negative, so they will cancel each other out. So we get a 0. And I guess for this case, I say this convergent integral right away. So doesn't matter. You have this infinity on the top or infinity on the bottom. It's still pretty much the same story. And I guess that's pretty much all this entire section has. I think that's very interesting and impressive, right? So exercises in this section will be utilized pretty heavily in the next chapter. And I guess I'm not gonna get very deeply into it because it's all about finding antiderivatives. So I guess if you just look at the first group of problems, it'd be good enough. What else they worrying about? Well, in picture such as exercise 76, notice that the region here is also infinite, because at x equals to 0, we have so-called vertical asymptote, right? And in that case, we need to also integrate improperly. The reason is when you find the antiderivatives, then, so if you try to integrate minus ln of x, how would you integrate that? Well, it looks like we don't have such a antiderivative, so our favorite parts, right? u dv, that's uv minus integral of v du. That's how we integrate logarithms. Or some people just remember we had this tables idea, so some people just memorize those tables, but I don't think it's a good idea because you'll remember it for a month or two, but then over summer most likely forget if you don't use it. So derivative of ln is 1 over x, so I put a minus still present with dx. That's du, and then x is v, right? X is v. Okay, so now we go uv, so we multiply these two guys together, and that'd be a minus ln of x times, instead of v, I put just x, and then we subtract integral of v times du. So now we take v, which is x, and du, which is going to be all of that, minus 1 over x dx. Right? And x's will cancel, and that makes me always happy. I love cancel. So we have to just integrate 1, and that will give us x. So we have minus x ln x and plus x and plus the constant. Now, notice that if you try to put integration from 0 to 1, then you're going to have to put 0 here. And the ln of 0 is undefined. I say, well, that's infinity. Well, we don't plug 0, we say it approaches to infinity. But we're actually going to utilize this improper integral and see if it's actually infinity or maybe not. And that's the key point in here. So even though we can find that antiderivative, but we should still go with that letter B. And now that B is going to be approaching to 0 instead of approaching to infinity. So I go from not 0, but from B to 1. And the limit of this was B approaching to 0. You see, that's the similar trick. And then I integrate minus ln x dx, and I already know my antiderivative, what it came out to be. It's right here. So it's a negative x ln of x and plus x. And now I go from B to 1. And then I will take my limit when B approaches to 0. And it may happen to be not an infinity, so it depends. So let's see what this is in my case. So ln1 is here, that is 0, plus 1, that's my upper value, minus, and then at the lower value, we get a b ln of b, and then plus x, which is b once again, right? And the limit when b is approaching to 0 to be taken. So first piece is 1, right? Because this goes away since it's 0, so it's a limit of 1. Minus and minus is plus. Now I'm taking the limit of the other piece. So question is, how can I find that limit? So I'm gonna think of limit of, see, this piece approaches to 0, but that one approaches to infinity. So I need to somehow prepare this. And the way I want to prepare it is to write it as ln of b over 1 over b. Because this way, I'm going to have the numerator that goes to infinity and denominator that goes to infinity. And that's the L'Hopital's rule story that we just saw in the previous section. And that b is just turning into 0, so don't write it. So the question is, we probably have to get rid of this ln by using derivatives, right? So you're gonna take derivatives from the top and the bottom. So 1 is still here. So let's see what we're going to get after we take derivatives. So 1 over x is, or 1 over b, because b is our variable now, is here. And for a denominator, it's minus 1 over b squared, right? Derivative, b to the negative 1. So power is minus 1. And when I take derivative, it will be another 1. So it's negative 2, and the minus goes in front. So when I say, Alex, is still infinity over infinity when you get b equal to 0. Yes, but why don't I now simplify this a little bit? So then I can find the limit a little bit easier. So I get the negative because of denominator, right? And then limit of b to the second divided by b to the first. So after they cancel, then we have what? 0, isn't it? Because it's just a limit of b, and b goes to 0, so this stuff disappears. And look at what I found. The area is 1. So this limit is 0. You can double check this on your own. I think it'd be a good idea. You can use L'Hopital's rule. Some people can say, I like L'Hopital's rule. So I put 2b over 1. So it's 2b, b goes to 0. So just 2 times 0. So there's 0 any way you like to take it. But the point of story, then that integral has area 1. How about that? So the area of this infinite region is actually not infinity, as some people could say. Oh, it's ln of 0, which is infinity. Well, but there is still another 0. So it's a 0 times infinity. That's a undeterminate form. Undeterminate means it could be anything. So we use L'Hopital's rule in order to determine it. So this situation is also possible. And I guess it's good to be aware of it. My point is just make sure that you see this section, and we'll be revisiting these ideas quite often, again and again. And maybe you can revisit one right now and try exercise number 19 as a little quiz for today. So try to find the answer for this exercise. And I did a similar one with x to the power of 5. I just did 20, right? So please try number 19 without a hurry. And as usual, put the answer in the chat. And I also want to tell you that I received work from most people in class, sent me work and made me very happy because the result on the midterm was good, and I would say very good. But I'm still waiting for work from a couple of people. I don't know what happened, but I truly hope to receive it. So I'm waiting and given another chance. And I send emails. So send me if something here that you owe me, just send me. But again, I think everyone did it very well. And I would say final should be in the same format. It looks like it works for pretty much everyone in class. So this way, I guess you will get pretty much the same grade on the final. And I guess that's our plan for next half of the semester.
Professor, I emailed you my work long time.
Oh, let me double check it, because I sometimes have people that not getting this or have different names when they log in. Let me double check everything, because
Okay.
I want to make sure, because I see your name written here for me by pen. Maybe I got mixed up. So let me double check this right now. So let me work it. Thank you for letting me know. So let me go to this list right now. So see, maybe I wrote you twice, and maybe that's why I just asked you this question, because I don't think that when I was putting on the canvas there was any issue, but let me double check. So let's see.
Did you send out the email about like the homework, and I sent it to you.
No, no worries, no worries. I just want to make sure right now. So let me see what is going on, because it would be on my side. But it's great that we're taking care of it. So let me go there. So takes a little time. That's why I just need another minute or so.
I sent it to you on March 2.
Okay, so let me see what is going on, because
You responded to the email. You said thanks.
yeah, I just looking at the list of students. So let me see what is going on, because something is not clear for me. Let me clarify. So let me go to Canvas and try to find your name. You check the Canvas, right? So
Yes.
let me go to courses, because I just have something. Oh, I see. Your last name is, I have a Tyler, but that's
No, that's part
Mendoza.
of
Yeah,
my
that's
first
why. That's
name.
the reason why. Now I see. Now I see. Because, okay, because you see, when you sent me a message, I get this by the name and the Zoom, and that's the reason why I asked. So great, great. Now we're clarified. I made myself a correction. Perfect.
All
Thank
right.
you. Yeah, that's what I thought, because the assumption was not clear, and I just, okay, great that we found out. Yeah, you're good. You're perfect. Thank you. Thank you.
Okay.
No worries.
You found my work though, right? The
No, I
homework.
have everything from you. I just have it under the last name Mendoza. That's why it's.
Correct.
That's why I asked this question. But good, good. So now I put it on my list. Okay, good.
Okay. Thank you, Professor.
Oh, no problem. Thank you. Thank you for clarifying.
All right. See you Wednesday
Bye bye.
or Thursday.
Thursday. Yeah, Thursday. Thursday is the way to go.
All right.